Hey guys, in all the lectures that preceded our discussion on nonlinear ODE, the starting point was, or the material behavior that we considered was something along the lines of the permanent damage that was introduced to a crystalline material. We assumed ourselves to be walking across a path wherein we stumbled across a bike with a bent wheel, and we wanted to understand the material behavior that is responsible for this bent wheel. Now this was the starting point for our discussion on ordinary differential equation, and we brought about some changes to this consideration in order to develop or introduce the different forms of ODE. And only towards the end we consider a different material behavior. Apart from that, and towards the end meaning only when we consider the nonlinear ODE, we considered or we included or we introduced a different material behavior. Apart from that, all the discussions on ODE basically stemmed from the permanent damage that was introduced to the metallic rim of our bike. Now in this and in the upcoming lecture, we will be considering a different mechanical behavior, even though it could also stem from the bent wheel. Now what we essentially would like to do is, we would like to, as a starting point, we would like to make things personal. Instead of talking about a random bike with a bent wheel, let us imagine that we own this bike and there is one friend who intentionally wants to damage or introduce a permanent damage to this bike, particularly the metallic rim of this bike. Now, being someone who is interested in the metallurgical aspect of things and the material aspect of things, and who is rather keen on researching in this metallurgical and materials behavior, what we want to do is, we want to ensure that the rim of the wheel is sufficiently hard so that when my friend intends to permanently damage my rim of my bike, it is not the metallic rim that gets permanently damaged, but rather it's my friend. So this is what the objective that we are working towards. We want to ensure that the rim of my bike is sufficiently hard so that when my friend wants to damage it, it no longer gets damaged, it pushes back. It's sufficiently hard so that's not to take in any damages. So that is what our objective is, and that is what we want to do. In order to achieve this objective of having a bike with a metallic rim that is sufficiently hard to withstand any damage that could be imposed by my friend, what we do is, we take this rim of the bike and we place it in a container and pack this container with carbon rich material. So let us assume that the rim of my bike is made up of steel, and in order to ensure that my steel is sufficiently hard to push back any permanent damage my friend wants to inflict on it, I take this rim of my bike made up of steel, place it in a container and pack it with carbon rich substances. Let's just assume that the carbon rich substance that I use is rather coke. So this is my container. I'm placing my metallic rim within it and pack it with carbon rich substance. Now what happens is, I take this container, raise the temperature of this container and hold it for a prolonged period of time. And once after holding it for a prolonged period of time, and when I measure the hardness, when I test the hardness of my metallic rim, I find that the hardness of my metallic rim, after being placed in this container, packing with carbon rich material, raising the temperature and holding it for a prolonged period of time, after doing all this, when I measure the hardness, when I consider the hardness of my rim, I find it to be extremely high when compared to that of my original rim. Now when I observe this, I want to understand three different questions that stem out of it. One is, what has happened that has increased my hardness of my rim significantly? So that is one question I want to understand. What has happened to my rim so that the resulting hardness is significantly higher? The second question I want to understand is, why has this happened? So there is some material behavioral change, or there is some change that has been introduced into my material, and this has increased the hardness of my material. I want to understand what it is. The second question I want to answer is, why has it happened? Now this what and why, this material behavior of what and why, I want to then express it in a mathematical framework, and then I want to solve it, and I want to understand how much relevant it is for me to place it all in a mathematical framework and then solve it. So these are the three questions I would like to answer. I want my material to have increased hardness. I do something. I want to understand what is happening such that the material hardness is increasing. The second thing is why it is happening. If at all this being a mathematical technique course, if at all I take this what and why and translate it to a mathematical framework and I solve it, I get some expression, is it worth it? Is it relevant? If relevant, how can I use it in this framework? Is what I want to get an answer for. Now, let us begin by answering the question what. So if I assume that, in my case, if I assume that my rim is made up of steel, my concentration of carbon when compared to my rim is considerably higher in my surrounding. So when I consider the difference in the carbon concentration between the rim of my bike and the surrounding, that is what surrounds my rim of my bike within the container, the carbon concentration is significantly higher. Now, in this context, when I rise my temperature and then hold my container at that temperature for a prolonged period of time, it is as if the carbon atoms in my surrounding have gained sufficient energy and now they are allowed to percolate into my steel rim. I raise the temperature of my container with carbon-rich surrounding and my rim, and when I hold my container at that high temperature for a prolonged period of time, the carbon in my surrounding has gained sufficient energy and then it begins to move into my metallic rim. Now this movement of my carbon from the surrounding to that of my metallic rim essentially increases the carbon concentration in my metallic rim, thereby ultimately increasing the hardness of my material. So what causes an increase in the hardness of the material is increase in the amount of carbon within my metallic rim. And what increases the amount of carbon within my metallic rim is the movement of carbon from the surroundings to that of my steel rim. When this happens, the carbon concentration within my rim increases and ultimately my hardness increases. So then we have answered what is responsible for the increase in hardness. Now we have to understand, or we want to understand, why is this happening? Of course, there is a movement of carbon, but what proposes? Why is this happening? Now, in order to understand that, we consider a one-dimensional section of my container. I consider a one-dimensional section of my container, AB. So AB is just a one-dimensional section of my container that is representative of my entire container with the carbon-rich surrounding and my rim. Now, across this one-dimensional line AB, I would like to consider how the carbon is distributed. Across this one-dimensional line AB, I would like to consider how my carbon is distributed. The point where as I move along AB, I move away from steel into my surrounding is C. So I'm moving along the line AB, and as I move as I come to C, the C is the interface that separates the rim from that of my surrounding. The C is the place where my rim ends and my surrounding begins. Now, when I plot the carbon concentration across AB, I end up getting a profile like this. Wherein within my rim, the carbon concentration is low, and as I move into my surrounding, it shoots up and continues to remain high. As I move within the metallic rim, my carbon concentration is low, and as I move into my surrounding, it is extremely high. And this point wherein the transition happens is the point C. So as I move away from, or as I slip away from my rim and move into my surrounding, my carbon concentration shoots up. And this is the initial carbon concentration profile at time 0. So what we are essentially doing is we are plotting our carbon concentration across the section AB, and when I walk across the section AB, initially I walk across a lower concentration region, and once I reach C, I move into my surrounding and my carbon concentration shoots up to be high. Now, when I raise the temperature of my container and hold it at that temperature for some time, what essentially happens is the system wants to reduce this difference, this disparity in the concentration. Therefore, some amount of carbon from the carbon rich surrounding moves to the carbon low rim. So as I increase my temperature and hold my system at high temperature for a prolonged period of time, some amount of carbon moves from the carbon rich surrounding to the carbon deficit rim. So then what happens after a given time t is, in some region the carbon concentration decreases, and whatever amount of carbon concentration is decreased, it's getting increased in the rim. So whatever carbon the surrounding loses, that amount of carbon is gained by my rim. So in this area, when compared to the original carbon concentration, when compared to my original carbon concentration, the amount of carbon has decreased. And in this area, which is within my rim, when compared to the initial carbon concentration, my amount of carbon has increased. So what essentially pulls or propels my influx of carbon atom or carbon concentration is this disparity in the amount of carbon when I move across the rim to that of the surrounding. There is a significant disparity in the carbon concentration. And when I increase the temperature and hold my system at high temperature, the carbon wants to reduce this disparity. The carbon moves from high carbon concentration to that of my low carbon concentration, meaning the carbon moves from the surrounding to that of my rim. So as the carbon concentration decreases in the surrounding, as it moves into my rim, the carbon concentration decreases into my surrounding, and the corresponding degree, the carbon concentration increases in my rim. So this is what dictates the increase in the carbon concentration within my rim. So I see there is an increase in hardness in my rim when I do this, when I place it in a container packed with carbon rich material, increase the temperature and hold it for a prolonged period of time. I see that there is an increase in hardness. The reason is because the concentration within the rim increases. The reason why the concentration within my metallic rim increases, is because there is an influx of carbon from the surrounding to that of the rim, primarily driven by the disparity in the carbon concentration. When compared to the carbon rich surrounding, the carbon within the steel is significantly lower. So in order to reduce this disparity, the carbon moves from the carbon rich region to the carbon deficit region, and this increases the amount of carbon in my rim, ultimately rising the hardness in my metallic rim. Now, what we want to understand is, if I take all this material behavior, that is the movement of carbon from carbon rich to carbon deficit region, and if I express why it is happening, and take both these answers and express it in a mathematical framework and try to solve it, will this be relevant is the third question we want to answer. We know something is happening. We know there is a diffusion of carbon. Now we understand why there is a diffusion of carbon, or what propels this movement of carbon, this influx of carbon. If I take this, I present it in a mathematical framework, and then I solve it, what is the relevance of all these things that we are doing? If I place it in a mathematical framework and I try to attempt to solve it, what is the relevance of this mathematical solution that I get in what I am considering is the third question. Now, in order to answer the third question, let us consider what will be the variable I'll be dealing with if I discuss this influx of carbon, this increase in hardness, and why it moves into my metallic rim. If I discuss all this in the mathematical framework, what will be the variable I'll be dealing with? Now, the principal change that happens during this process is the concentration or the carbon concentration. Now, when my time t is 0, I find that as I move along AB, when my position changes, my carbon concentration is correspondingly changing. At time t0, when I move from A to C, that is till the end of my rim, I find that my carbon concentration is at its lowest, and I move away from A to C, it is maximum. So what I have is my carbon concentration is dependent on my position, where I stand within my container, and depending on it, my carbon concentration is going to vary. And not only that, but when I consider different time for the same position, even in that case, my carbon concentration is varying. So let us consider this spot here. Let's say a spot D. When time t is 0, at spot D, when my time T is 0, at spot D, my carbon concentration is low. Now, instead, at the same spot, if I consider my carbon concentration at time T1, which is this curve here, I find that my carbon concentration is no longer low, but it is greater than low. My carbon concentration is greater than low. So essentially what I have is my carbon concentration at a given time depends on its position. And now when I fix my position and vary my time, my carbon concentration still changes. So essentially my carbon concentration changes with both time and also with respect to my position. So when I take this material behavior, place it in a mathematical framework, and then when I solve it, I end up getting a solution that helps me understand what will be my concentration at a given position and at a given time t. So this is what the understanding that I would gain if I take this entire material behavior, place it in a mathematical framework, and I solve it. Now, if there is any relevance to this expression that I have, that is how carbon concentration is going to change with respect to my position and time, then it essentially answers my third question. So when I'm able to understand the relevance of arriving at an expression for carbon concentration at a given time and a given position in my space, then I will be able to understand the relevance of doing such or performing such an operation wherein I'm translating everything or putting everything in the mathematical framework and solving it. Now, this type of variable which changes with position and time is what we generally refer to as the spatiotemporal variable. So spatiotemporal variable means a variable that changes both with position and with time. Now, in order to understand the relevance of the gaining or ascertaining the concentration at a different position and different time, let us consider a position, say here. Let us consider a position that is at the end of my rim. Now, when I'm tracking the position of my carbon concentration at this point here, what essentially I would observe is there is an increase, a gradual increase in the carbon concentration with respect to my time. So I have my rim in a container that is packed with carbon rich material. I'm increasing my system to a high temperature and holding it for a prolonged period of time. So what I choose to do is I choose a point within that metallic rim and I monitor the change in the carbon concentration. What I would essentially observe is there will be a gradual increase in the carbon concentration as my carbon begins to move in, and after some point the carbon concentration begins to remain same. After some point the carbon gets saturated, and beyond which there won't be any influx of carbon. How much ever long I hold my system at high temperature, my carbon concentration is going to remain constant beyond certain point. If I assume that the temperature to which I'm raising my system is constant, it is known to me, the only variable that I can play with is time. When I have a prolonged time, when I expose or when I hold my container to high temperature, at high temperature for a prolonged period of time, the expense or the factor that governs the amount of money I spent on this process is how long am I holding my container at high temperature for. So that is the only parameter that decides how much should I have to spend on this process. Now, supposing if I'm able to calculate that at this point my entire rim is saturated with carbon, then at that point I would be able to stop my operation. Let me repeat. When I'm taking my container with rim packed with carbon rich material and holding it at high temperature for a prolonged period of time, if I'm able to say that at time say Tf my entire rim is saturated with carbon, then I can stop this holding period at that specific time so that I'm being efficient. Any time beyond Tf is going to be rather redundant because there is not going to be any more influx of carbon. So the optimal time I have to stop my operation is Tf. This point I will be able to understand, or I will be able to determine if I know how my carbon concentration is changing with respect to my position and time. Now, if the point that I have chosen is the last point for the carbon, is the last point where the carbon would reach, and I know that this is the time it would take for the carbon at that point to reach the maximum level, then I can safely say that all I have to do is hold my high temperature container for this amount of time, and there will be a homogeneous maximum distribution of carbon. So when I want to plan my operation, so this operation is referred to as the carburizing, or let's say it's just a heat treatment process. So when I want to rather plan my heat treatment process, and I want to be extremely efficient, meaning I don't want to even hold my container beyond the time time which is required to achieve a homogeneous maximum distribution of carbon. I don't want to even hold at that high temperature for a second more. If I want to be so exact in the planning of my heat treatment process, then it is efficient for me, it is ideal for me to know this particular function, so that I can calculate how much time will it be required to achieve a homogeneous maximum distribution of carbon within the run. So in this way, understanding how my concentration is going to change with position and time will help me plan this heat treatment, this entire process here, in an efficient manner. So what I mean by efficient manner is I can hold it for an exact amount of time, not a second more, so that I'll be able to achieve the homogeneous saturated distribution of carbon within the rim of my bike. So we understood what is happening that causes the increase in the hardness. We have an idea of why it is happening, and now we see the relevance, because it helps us in a macroscopic scale, in an actual industrial scale, to plan our heat treatment efficiently, not to hold or not to spend any more amount of energy in holding my container at the high temperature. I can hold it for till the exact moment wherein I am able to achieve a homogeneous maximum distribution of carbon. Knowing this relevance, we will now try to build a mathematical framework that describes this particular behavior, and then we will try to solve this in the subsequent lecture. Goodbye, guys.